So in this video, we're going to go over what are the different relationships of graphs. And then let's say we have a relationship, what graph do we plot in order to find these constants? So first thing I look at is, let's say I've got this graph and I'm trying to figure out what relationship it is. Hopefully straight away you look at it and we know that it's some type of basically decline graph, right? So things I might be thinking of is that it might be inversely proportional, that y is directly proportional or inversely proportional, to 1 over x. Okay, clearly we know it's not directly proportional, because if I was to do a directly proportional graph, we know that'd be a straight line for the origins. That'd be my y is proportional to x, right? That's my directly proportional relationship. But this is something that's dropping over time, so I'm saying y is inversely proportional to x. So let's say that's what I predict this graph to follow. How do I prove that? To prove it, what then is, all right, y is equal some constant divided by x. So if I want to determine what that constant is, I can write y times by x equals some constant. So if this is true, and that really is the relationship of this graph, I should always get a constant when I do y times by x. So let's look. Let's say my x value is 1, and we go up to see what our y value is. It's going to be 70. So when our x value is 1 and our y value is 70, when we multiply them together, we get 70. When my x value is 2, my y value might end up being, say, 61. So 61 multiplied by 2 is going to give me 122. 61 multiplied by 2 is 122. Let's say then we do a third value, but I don't even need to do a third value, right? Because clearly we can see this is nowhere near a value of a constant. So clearly that is not my relationship for this graph, okay? So let's say maybe I want to say that y is proportional to, or inversely proportional to 1 over x squared. That could be what the graph looks like. So now I'm going to say that y equals some constant over x squared, or y times by x squared equals a constant. Okay, so if this is true, I should always get the same constant. So take my y value again, we said was 70, my x value was 1, and we're going to square it. 70 times 1 squared is going to be 70. This time again, we take our y value, 61, we're going to take our x value and square it. So I'm going to do 4 times by 61, which is going to end up being 244. So again, clearly we're more off, right? That's nowhere near the right relationships. So what you think now is what might be the other type of relationship, the other type of form of this graph. And you might think it might be an exponential graph. Okay, so maybe I'm thinking it might be y is equal to ax to the power n, some type of exponential graph, right? So what I want to do now is I want to see, is it exponential? The best way to see if it's exponential or exponential decay is think about when you did physics in GCSE and you think about half-life, right? Half-life is an exponential decay. Okay, so in half-life, what we did was imagine if that number was 100, what we did was we seen where it drops to 50, we went across and we seen that what time was. It was 2 seconds. If we know the half-life is 2 seconds, when we do another 2 seconds to get 4 seconds, I know that value is dropped by half again to get 25. So for an exponential decay graph, what we can see here is for equal increases in the x-axis, what we had was the y value dropped by equal amounts, right? The y value was always dropped by 2. It was always divided by 2 or multiplied by 0.5, multiplied by 0.5. Okay, so for equal increases in the x-axis, we can see there's an equal drop, an equal magnitude of drop in the y-axis. So what I'm going to do now is I look for my equal increases in my x-axis. So let's go from 0 to 1. So from 0 to 1 on my x-axis, I can see my y value dropped from 80 down to 70. Okay, so I want to see when it dropped from 100 to 50, 50 divided by 100 is 0.5. So when it dropped from 80 to 70, if I do 70 divided by 80 to see what that magnitude of drop was, I can see it was 0.875. Okay, so same thing, 50 divided by 100 is 0.5, 25 divided by 50 is 0.5. It's dropping by an equal interval each time, an equal factor each time. So let's do another interval. Let's go from 1 to 2. Get an equal interval in time. So we go from 1 to 2. At 1, my value was 70, and now it's dropping down to, say, 61. So again, to see what that factor was, I do 61 divided by 70. So when we do 61 divided by 70, we get 0.871. Okay, so this looks pretty good so far, right? But to prove a relationship, you need to always do a minimum of 3 times. So I need to do a third time. So let's go to 3. So here, another 1 increase. So what we're doing now is we're going from 2 to 3. So So I got another 1 increase. I go to 3 and across to see what it says. Roughly it says what? Maybe like 52, 51? What do you want to say? Like 52. So we're going to die from 61 down to 52. So what I do now is I'm going to do 52 divided by 61 to see what that value is. So 52 divided by 61 gives me 0.85. Okay, so if I look at this, all those numbers are really close together, right? Look at these ones. They're very different, whereas these numbers are close together. If I write all this to 1 decimal place, that's 0.9. 1 decimal place, 0.9. 1 decimal place, 0.9. So to 1 decimal place, that is a true relationship. It is going to be an exponential decay. Sorry, ignore that. An exponential decay. That is for this graph. Okay, so what I wrote here, y equals ax to the n, what that is say we don't know what the relationship is. Y equals x to the n is always what we model the relationship to be. Okay, so y x to the power of n. Okay, let's say it doesn't do anything to the power of n will be 0. That's y equals a times x, okay, or constant times by x. So again, if it's an exponential decay, this is the steps we do. So remember, exponential decay is like e to the negative x. Okay, again, so equal different intervals in our x-axis, equal drops in the y-axis. So we just proved it's exponential decay 3 different times to 1 decimal place. Okay, for this, that shouldn't rubbed off, sorry, because I still need it. This one is look at this relationship. So anytime maybe we don't know what the relationship is, we can model it like this. Okay, so what we can do is we can find out what the a is, find out what the n is by plotting in a graph. So just to show you this here, where it came from, let's say we had y equals ax to the power of n. If I wanted to find out if that's what that relationship is, because let's say n equals 0 and y equals a to the power of x, or y over x is equal to a. If you look there, y over x is equal to a, or y equals some constant times by x, y equals some constant times x, we can see that that is going to be some type of graph that would be directly proportional. Okay, so again, we can use this as a model for all equations to figure out which one of these relationship it is. Because if n becomes 0, so if we do data and find that n is 0, we can see that y equals some constant times by x, so that would be our directly proportional relationship. If n equals squared, so let's say we do the relationship and n comes out to 2, y equals ax squared. What I can see now is that it's going to be an x squared graph. So we know an x squared graph would roughly look like that. So again, this is just our equation we use to model all an unknown, basically. So say we have some equation, we don't know what it's going to be like. That's what we use to represent it. Okay, so how does this apply to this? So let's say we've got some experiment. We've got some height, initial height h of our water in our tube. We've got h, the height it is right now, and we know that it's going to drop over time. And it says that it's going to drop according to this decay constant and the time that we're recording, and our capital H is our unknown constant. The question wants us to say, how are we going to find out what these two constants are? Okay, so it's basically asking you, when you do this experiment, what are you going to plot in a graph in order to find out what the two constants are? So if this is my equation, I know when I will plot a line, I need to get in the form of y equals mx plus c, right? So that looks nothing like y equals mx plus c. So what we need to do here is take natural logs of both sides. So if I do the natural log of h, it's going to equal the natural log of h e to the minus lambda t. Okay, the first rule of natural logs that you need to know about is that anytime you multiply, what means is you're going to add them. So for example, if I have log of a times b, that's the same thing as saying log of a plus b. Okay, so you might see log, that's the base 10. If I have the natural log of a times b, same thing as the natural log of a plus the natural log of b. Okay? We don't use logs to the base 10 in physics, basically ever. We mostly always use natural logs. And what natural log means, it's got the base e. You'll see that in your calculator. So that button ln, and it's got to the base e. And the reason we use natural logs or logarithmic graphs is because sometimes it might not be a scale where it goes up quite nicely like this. It might be a scale where when you take out loads of data, it might be that you've got the number 1,000 to plot, and then you've got the number 2 to plot, right? You're not going to squeeze all that data onto one scale, so that's why we use natural logs or logarithmic graphs, because I can get more data onto my scale then. Okay, so what we said here is when we multiply, we add them. So what I've got now is my natural log of h equals the natural log of capital H plus the natural log of e to the minus lambda t. Okay, the next rule that you need to know, and this one always comes up in physics, is that any time that you have natural log of e to the power of anything, it just equals what the power was. So again, if I have natural log of e to the negative x, it's just going to equal negative x. If I have natural log e to the power of t squared, it's just going to equal t squared. So here, if I have natural log of e to the minus lambda t, it's going to equal that power. So natural log of x equals natural log of capital H minus lambda t, right? Natural log of e to the negative x just becomes negative x. Natural log of e to the negative yt just becomes negative yt. So now I can see I'm starting to look like this form, y equals mx plus c. So let's say I want to do natural log of h. I need two things multiplied together. There's my two things multiplied together. So I'm just going to rearrange this equation, minus lambda t plus the natural log of h. So what I can see now is my c, my y-intercept, is the natural log of h. So my y-intercept is going to be the natural log of h. And I can see m, my gradient is going to end up being what that constant is. Because clearly I'm going to plot time on my x-axis because that's what I'm recording. So if I want to plot this on my graph, we'll see that we're going to get something that y equals mx plus c. The gradient is going to be negative lambda. So it's going to be a negative gradient, negative lambda. So again, I know that gradient is going to equal negative of whatever that decay constant is. Okay, so the reason we find out what h is to find out h, it's not just taking the y-intercept. Remember, the y-intercept, that value c, is where it crosses the y-axis. So you can't just say it's the y-intercept because it's not, right? The y-intercept is the natural log of h, okay? So what we're saying here is that the natural log, the base e of h, equals the y-intercept. Okay, the question wants to say, how do we find h? And this is where you have to know another natural log rule. So another rule that you need to want is, let's say we've got log of a to the base b equals c. You just want to learn to write this in your test. If you have b to the power c, it's always going to equal a. Okay, so just to show you how that works. Let's say I have log to the base b of a equals c. There's my log, there's my base b of my a equals c. The b, which is my e, to the power of c of my y-intercept equals my a, which is h. So if I want to actually say what h is, I have to take e to the power of my y-intercept. So my actual answer here for what h is, so final answer is to find h, I take e to the power of the y-intercept. So what you do then to get that value e is in your calculator, you just hit shift of that natural log button and you'll plug in what the y-intercept value is, what that value is, and that'll give your actual value of h. Okay, a lot of people just want to write down that h is the y-intercept, but again, it's not. It's the natural log of h is the y-intercept. Okay, next one, if I want to find what the decay constant is. Again, I can't just write that it is the gradient because it's not the gradient. The gradient is negative the decay constant. So if I want to find what that decay constant is, I have to take negative of the gradient.